We've now investigated trajectories on the chessboard of pressure versus volume. And the most important thing is to examine the interchange between the change in internal energy, the change in enthalpy, the work and the heat along each one of these trajectories. So we're going to work this out, and this is the most important way of relating U, H, work, and heat. And once we've finished this, it's probably the most important combination of interrelationships in thermodynamics. So let's get started. So let's first of all work on the change in internal energy, the thermal energy of the system for our 4 different trajectories. So the first thing we do is write down the first law of thermodynamics, because it's remarkable how that'll clarify these calculations. Well, if the pressure is constant and delta P is equal to 0, then we can write this as the heat at constant pressure minus P delta V. But we can write the heat required at constant pressure, that's simply the number of moles times the specific heat capacity at constant pressure times the change in temperature. And let's just keep notes down here. Let's agree that the difference in temperature, T final minus T initial, is always going to be written delta T in this, because if I write T final minus T initial out, it not only consumes time, but it also consumes space. So we're going to confine ourselves to that representation. All right, now I have minus P delta V. But the next note I remember is that PV equals nRT, because this is a perfect gas. So P delta V is simply equal to minus nR delta T by using the perfect gas law. Well, I can then recognize the fact that I have N C sub P delta T minus nR delta T, and I come back to the fact that I have deduced already a relationship between molar specific heat at constant volume and that at constant pressure, namely that C sub V plus R is equal to the molar specific heat at constant pressure. Well, that means that C sub V is equal to C sub P minus R, and that's exactly what I have in my expression for delta U under constant pressure conditions. So if I write this now as N delta T times C sub P minus R, that's equal to N C sub V delta T. Well, that's very reassuring, because when we go all the way back to our bomb calorimeter, when we were measuring the energy release from a chemical reaction by confining that chemical reaction to a volume that didn't change, in fact, we deduced exactly that relationship. The delta U is equal to Q at constant volume, Q sub V, which is to say delta U is equal to Q sub V at constant volume. Okay, now let's move on to the isochoric case. In this case, volume is equal to a constant. The change in volume is equal to 0. So when we write the first law, we have delta U is equal to Q plus the work term. But if delta V is equal to 0, there's no mechanical change in that trajectory, and so the work has to identically equal 0. That means that delta U is equal to Q at constant volume, but Q at constant volume is equal to NC sub V delta T. We just worked that out on the trajectories. And so that gives us immediately a calculation of what delta U is for the isochoric trajectory. Now we're moving quickly, because we're going to consider the isothermal trajectory. Now this one is particularly interesting, because if T is equal to constant, delta T is equal to 0. But I can write my expression for the internal energy as the number of molecules times 3/2 Boltzmann constant times the temperature, which means that delta U is equal to N 3/2 Boltzmann constant times delta T. Aha! But delta T is equal to 0. That means that delta U is equal to 0. And that means that delta U, first law of thermodynamics, Q plus W is equal to 0. And that means that Q and W are identical in their magnitude but opposite in their sign. All right, the adiabatic case, Q is equal to 0. So delta U is equal to Q plus the work term. The heat exchange between the system and surroundings is 0. And that means I can immediately write the fact that delta U is equal to the work term. But we've just calculated what that work term is along an isothermal surface. The work term is equal to delta U, which is equal to the number of moles times the molar specific heat capacity at constant volume times that change in temperature. So notice that we've been able to apply that fundamental principle that because U is a state variable, we can always calculate delta U between any two temperature points. Now let's look at enthalpy. Enthalpy, we know, is equal to delta U plus the pressure times the volume. So I take the change in pressure times volume. But I also remember that PV equals nRT. So I can immediately write the fact that delta H is equal to delta U plus nR delta T. Well, we've just calculated what delta U is, but we also remember that the definition of delta H was the heat release at constant pressure. So I can write this as Q sub P, and that's equal to NC sub P times delta T. And that allows me then to calculate delta H. Now let's move to the isochoric case. Let's take our constant volume case. Now we write out our delta H as we did before. That's equal to delta U plus the change in the product of pressure times volume. That's going to be equal to Q at constant volume, because I can extract that directly from my conclusion for the calculation of delta U. But then I have plus the change in the product of pressure times volume. That's simply equal to nR delta T. All right, but we know what the value of the heat at constant volume is. That's Nc sub V delta T plus nR delta T. And lo and behold, when we use our relationship between CV and Cp and R, this collapses down to give us identically that this is Q at constant pressure, which is then equal to Nc sub P delta T. All right, now the isothermal case. So we write our delta U is equal to Q plus W. We recognize that it's isothermal, so that's equal to 0, so that Q is equal in magnitude but opposite in sign to the work term. And so we have delta H is equal to the change in the product of pressure times volume, because we know that delta U is equal to 0, so it drops out of the first law, and lo and behold, we have delta H is equal to nR delta T, but delta T is 0, so delta H is identically equal to 0 for the isothermal trajectory. Now, the adiabatic pathway. So we have delta U is equal to Q plus W. If Q is equal to 0, then the work term is identically equal to the change in internal thermal energy of the system. And we know exactly how to calculate that. That's the number of moles times the specific heat capacity at constant volume times the change in temperature. That's equal to delta U, but now we want delta H. And delta H is equal to delta U plus the change in the product of pressure times volume. And when we work that out, that's NC sub V delta T plus NR delta T, and that gives us NC sub P times delta T. Okay, now those are state variables. We turn now to the calculation of work and heat. And as we'll see, when we apply thermodynamics to a heat engine, this particular matrix of calculated delta U, delta H, work, and heat for each of these trajectories is the foundation upon which thermodynamics is built for the calculation of the efficiency of heat engines. So now let's proceed with the work term. Isobaric, pressure equals constant. So I have Q plus the work term. But I know that the work term is equal to minus P times the change in volume at constant pressure. But that's simply equal to minus NR delta T, because I've simply put in the perfect gas law for P delta V. So that was straightforward. Isochoric is even more straightforward, because if the volume is equal to a constant, that means that there's no physical work done. There's no macroscopic change that creates work by virtue of a force times a distance. So there's no distance, so that means that there's no work done. There's no macroscopic work done. Isothermal, delta T is equal to 0. All right, so now delta U is equal to Q plus W. And now this is where our previous work comes in extremely valuably. So Q is equal to minus W, but we calculated the work along an isothermal trajectory. That's equal to minus NR logarithm of volume final over volume initial. Very, very handy expression for work. Now, the adiabatic case. So delta U is equal to Q plus W. Q is equal to 0, so the work term is equal to the change in internal energy of the system. But I know how to calculate that. That's equal to the number of moles times the specific heat capacity at constant volume times the change in temperature. All right, now let's turn to heat, the heat term. So to calculate the heat along an isobaric trajectory, I know that this is equal to Q at constant pressure minus the change in pressure times volume. Well, I also know that Q at constant pressure is simply equal to the number of moles times molar specific heat at constant pressure times the change in temperature. So that's very straightforward. What about isochoric? Now, if V is equal to a constant, I know immediately that I can calculate the heat exchanged along that constant volume surface. That's simply the number of moles times the specific heat capacity at constant volume times change in temperature. Well, what about the isothermal case? Well, now we go back to our first law to remind ourselves that delta U is equal to Q plus W, but if delta T is 0, so too is delta U. That means that Q is equal but opposite in sign to work, but I've calculated the work term, so that means that I can immediately write down the heat term. That's just the negative of the work, so that's NR log volume final over volume initial. And then finally, the simplest of all, calculation of heat along an adiabatic trajectory, because Q equals 0, identically for an adiabatic process, we know exactly what Q is. It's equal to 0.